Hi everyone. All right, so we're going to start the thermochem unit. It's just chapters 5 and 19, so there's not a whole lot, and most of the unit is actually review, but harder problems. So as of right now, your test is going to be Monday, March 4th. All right, so don't plan any appointments or anything. All right. We're going to do all of Chapter 5 today except for 5.5 and 5.6. We'll discuss those when I get back. All right, thermodynamics, study of energy and its transformations. Now, thermal equilibrium is when two objects reach the same temperature. So, like here in this example, you've got System A and System B. System A is much hotter than System B. So, oh shoot. There we go. So System A is going to transfer some of its energy to System B, and it's going to do that until they're both the same temperature, okay? And then you're not going to have that heat transfer anymore because they're both the same amount of heat, okay? Now, in a perfect world, the amount of heat that is lost by System A equals the amount of heat that's gained by System B. Okay, so if it's in an isolated system, if it's all, kept perfectly, then yeah, the amount of heat that's lost here should equal the amount of heat that's gained by this one. In reality, that's not really going to happen. You're going to lose some heat, through the beaker or whatever, like to the surroundings. Okay. All right, so the system versus the surroundings. Your system is the thing that you're focusing on, and then your surroundings are everything else. The container that it's in, the atmosphere, you, and then the thermometer. Keep that in mind. The thermometer part is going to be very important later. All right, 3 types of systems. The first is an open system. So an open system is like just an open beaker, right? This liquid is going to be able to evaporate on its own. You're able to transfer energy through the beaker. That's very easy. So energy and matter go back and forth in an open system. In a closed system, so if we were to have a lid on this or cap this liquid isn't going anywhere. It's going to stay in there. It can't go anywhere, right? But energy can. We could heat this up. We could cool it down. Now, in an isolated system, energy and matter are both stuck inside of that system, okay? So you can think of it like putting hot coffee in a thermos. It's going to stay hot, right? So that would be an isolated system. Now, in reality, eventually that coffee will get cold, right? It's going to take a while, but eventually it will cool down. So a thermos isn't like the perfect example, but it's kind of the best one we can really think of, okay? It's really, really hard to get a truly isolated system. All right, so energy. 2 different types we're going to talk about, kinetic and potential. Kinetic means motion, right? Movement. So kinetic energy is the energy of movement. Potential energy is how much energy is being stored. So for your kinetic energy, your equation is 1/2 mv squared. M is the mass, and then v is the velocity. Those are inversely proportional. So the higher mass you have, the lower the velocity, right? So like the bigger these substances are, the slower they're going to be moving. You can transfer energy in 2 ways. Okay, work and heat. So work is when a force moves an object. So that's why your equation would be work equals force times distance. You're not really going to have to use that equation, but it's good to know. Heat is when it's transferring energy from a hot object to a colder object, and we are all familiar with that. Heat and temperature are 2 different things. Heat is energy. We also call it enthalpy, right? Temperature is a measurement of your average kinetic energy. Now, it's just an average, which means that if you have a sample that's at 50 degrees, remember that not every single particle is going to be moving at exactly that same speed for that temperature. Some of those particles are going to be moving faster, some are going to be moving slower. So when you take a measurement of temperature, it's just an average. But we know that the higher the temperature, the more energy it has, so those molecules are moving more. When you cool it down, They just don't move as fast because they don't have as much energy. All right, the laws of thermodynamics. Your conservation of energy. Energy isn't created or destroyed, right? Just like mass. But with energy, energy is transferred, right? You can transfer energy from one thing to another. Heat is always going to flow from warmer objects to colder objects. This is common sense. If you put an ice cube in your hand, okay, there is no way that that ice cube can get colder. Okay, that ice cube is only going to start warming up because you are warmer than it. And so your body heat is going to start melting that ice. Okay, now work can be done on or by an object. It's kind of like a push or pull situation. Okay, so this person is lifting up this box, right, and moving the box over here. He's doing work on the object by moving it over. Okay, when he goes to first lift it, work is being done by the object because that box is apparently a little heavy, and so it's kind of pulling him down. Okay, so just think of work as being push and pull. Okay, mathematically, you can relate energy in a system with heat and work. So your delta E, delta means change. So your change in energy equals your heat, which is Q. Think of Q equals MC delta T, plus W, which is work. Okay. So just how with Q, if Q is greater than 0, then heat's going into the system. It's endothermic, right? It's entering the system. If it's less than 0, then your heat is being released. It's exothermic. Work is kind of similar, okay? If work is greater than 0, then work is being done on the system, okay? If work is less than 0, then work is being done by the system. It's being done instead on the surroundings, okay? So it's similar mathematically. So let's do an example. You have gases A and B reacting to form solid C in this equation, okay? So as the reaction is occurring, the system is losing 1150 joules of heat to the surroundings. The piston is moving downward as the gases react to form the solid. Now this makes sense because if you have gas particles here and all of a sudden some of them are turning into a solid, well now those gases aren't taking up as much space, right? So that piston is going to move down. All right, so as the volume of the gas decreases, the surroundings, the piston, are doing 480 joules of work on the system. What is the change in the internal energy of the system? Okay, I want you to pause the video right now, and I want you to try doing this on your own. Go. Okay, hopefully you finished. You should have gotten negative 670 joules if you did it correctly. All right. Now remember that your delta E equals Q plus W. This number is representing Q. However, they're telling you that the system is losing that amount of heat, which means that this should be a negative 1150 joules, right? And then here it says that the surroundings are doing 480 joules of work on the system. So this is a positive number. All right, so your delta E is going to equal negative 1150 joules plus 480 joules, which will equal negative 670 joules. Okay, we understand? Like, you can't answer me, but I'm hoping you understand, so we're moving on. Okay, bond energy. We've already talked about this. We did this back in Unit 1, but I'm bringing it back. So, energy is stored in bonds between atoms, so that's potential energy. Okay, now bond energy is usually written in terms of kilojoules per mole, which just means it's the amount of energy required to break the bonds in 1 mole of a compound. So let's say we have carbon and oxygen and we're trying to make carbon dioxide. So you have this one carbon atom and you've got this oxygen molecule, right? Well, in order for these oxygens to bond with this carbon, you're going to need to break this bond between the oxygens, okay? In order to do that, it requires energy. You have to put energy into the system in order to break that bond. Think of activation energy. So now, you've got these broken atoms. Now you can put them all together and make your carbon dioxide. That is going to release energy. So when you make bonds, you're always going to be releasing energy. All right, so delta H, which is what we call enthalpy, okay, or change in heat. Now, you can use these bond energies to calculate the energy of a reaction. All right, think of it as bonds broken minus bonds formed. So we've done this already, okay? You can also think of it in terms of the energies of the old bonds plus the energies released when your new bonds are being formed. But remember that released means negative, okay? So that's why in general you want to use this equation, bonds broken minus bonds formed. Now you have this example. When you do examples like this, you're going to be given these values. You never have to memorize them. You'll always be given these values if you need them. So it says use bond energies to calculate the delta H for the reaction of methane with chlorine and fluorine to give freon. So here's your chemical reaction, okay? You need to figure out, using these bond energies, what the overall delta H is for this reaction. It will help if you draw out all of the Lewis structures here and then figure out which bonds are being broken and which bonds are being formed, okay? And then you can just subtract them. So you're going to do this problem right now on your note-taking guide, and then when you are finished, you're going to go open up the second video, okay? See you there.